regardless of the generation of technology. So 1600, 12, was 5-volt constant. And if you go back to the Dennard rule, it said everything had to scale, not only the linear dimension, the vertical dimension, but also the power supply. Because the industry was not doing that, what it meant was that the electric field between the drain and the source was increasing, right? You reduced the distance, but operating at the same voltage. So the electric field kept going up, and that was pretty stressful on the gate oxide. So down at half micron, 500 nanometers, people then started to reduce this to 3.3 volts. That was good for a couple generations. And remember I was saying when people were at less than half micron, it was called deep submicron, and that was the end of the world, right? It finally convinced the industry to go down to 2.5 volts, and then 1.8, and then 1.1, and nowadays is about 1, maybe 0.9 volts. Changing the power supply voltage is not easy because there's all kinds of power sources and other constraints at the board level. So it's not an easy thing to do, but that makes more of a challenge for the process engineers and the designers to design these chips. Since there's interest in analog, I would say that 180 nanometer technology is kind of a big workhorse for analog. It's only now that some of the bigger companies are starting to design analog at the 90 nanometer, 45 nanometer nodes, while digital is still at the 16 and 14. There are reasons for that. We're not going to get into that here. Maybe one of the other speakers will, but those are limitations. Okay, so why have people been talking about this doom and gloom? Here's a quote from Mark Bohr, who's a leading technologist from Intel, and he presented a paper at ISSCC 6 or 7 years ago. Here's some of the reasons. Optical lithography will reach its limits at 0.75 to 0.5. Remember I was telling you about that? Submicron can never be done. Minimum geometries will saturate in the range of 0.3 to 0.5. X-ray lithography will be needed below 1 micron. X-ray lithography is still way out there. Minimum gate oxide thickness is limited to about 2 nanometers. Copper interconnects will never work. Scaling will end in 10 years. Well, all those things have been negated. And so, like I keep saying, technically, solutions will be there. If you really stop and think about it, lithography is the way you take a design, transform that design into a photoresist, which then, photosensitive layer, which then converts that design and puts it on the silicon wafer. The wavelength of light that's used to pattern those features is actually 193 nanometers, and we are actually printing 16 nanometer, much smaller than the wavelength of light. That's the fundamental thing that people used to say that there's no way we can print dimensions smaller than 1 micron. So again, the industry has found all kinds of technical solutions. So extremely challenging, extremely exciting place to be in. If lithography is your passion, you've still got a whole bunch of stuff you can contribute to. Not just the patterning of it, but today people do, triple level masking to get the smallest dimension that you need to. Lots of challenges, lots of computation capability. It's not just about being a photolithography engineer in there. So pretty exciting field to be in. So technical challenges, if you think about this, lithography has been the biggest one, and we're still in immersion lithography, which is a 193 with is actually a drop of a liquid that the light goes through. I don't know if you're going to get into the core, but EUV is the advanced technology that's supposed to have been here. It still is not, and that could be the savior coming down, but so far things are okay. Metal gate, if you look at the cross sections of the devices, is a FinFET, is a three-dimensional structure, high mobility channels, and then looking ahead, there's all kinds of solutions that are being talked about for new device structures. One point I'll make is that when I entered the field in the 70s, I think there was maybe 6 or 7 elements of the periodic table that were used in semiconductor processing. Today, there are over half of the periodic table elements have been looked at, both at Intel as well as the R&D organizations for introducing into the mainstream silicon process. One point I'll make, though, is anytime you introduce a new element, it's a big challenge for us technologists, but it really requires extremely stringent certification and qualification in the process area in order to allow that to be used. And it's not easy, and that's one of the reasons why the cost of wafer fabrication has been increasing very, very rapidly. Another problem is that while people can't find the technical solutions, it is getting increasingly more difficult and expensive to do designs. By the way, it used to be in the old days, each transistor, 4004 Intel chip with 2300 transistors, designers would lay them out physically by hand and make the masks, right? With chips that are this complex, billions of transistors on it, you need automated tools. That's where Synopsys comes in. That's where Cadence comes in. You got to be able to simulate them. And I imagine Yervant's going to get into some of that information, what kind of tools that are used to do the design. But it's not just about the laying them out and connecting the transistors. It's about verifying that you didn't make an error. On a chip that has 10 billion transistors, you could have tens of kilometers of metal interconnect. You could have 10 billion vias. All those connections have to be verified physically that you're okay, that you haven't violated any of the rules. And then you also have to make sure that your performance is matching what your designer was expecting the performance to be. So these kinds of constraints require extremely sophisticated tools, extremely well verified models, and the idea being that the design has to be bulletproof before you release it to fab. Any idea why that is? A mask set could cost tens of millions of dollars at the 20 nanometer design. So if, let's say it costs $20 million to release a design with all the layers, and if there's an error, you got to change half the mask set, you got to trash $20 million in the bucket, right? So that's the reason verification is extremely important. About 60 to 70% of the design cost is said to be in verification. So if you were going to be a digital engineer, you could be a verification engineer, might be a good first step. Part of that is running the computer. Part of it is understanding what are the limitations. And again, kind of an exciting area to be in if that's your bailiwick. So what we said was design cost is going up. Every time you introduce a new element, your process cost is going up. To do a EUV or a 193 nanometer lithography tool set, do a new structure like 3D FinFETs, going to larger dimension wafers, all of that costs money. Using more elements of the periodic table, this is a cross-section of what the FinFET device might look like. This is across the picture of what an internal fab looks like. Very few people in there, a lot of automation, very, very expensive fabs. Anybody have an idea what it costs to build a high-volume wafer fab these days? Any guess? $1 billion? A high volume fab today costs $10 billion. Very, very expensive. That's why it's not easy. I don't know what the Global Foundries fab is going to be, the 22 nanometer FDSOI, but I would guess it's somewhere in the $5 billion range, 5 to 10. So this is what the chemical facility looks like on the outside. Very pure chemicals, liquids, gases, all those things. So very, very expensive business to be in, and that's the big limitation. So remember what I've been saying is technically we could find the solutions. Business-wise, it's not clear whether it makes sense to do this. And so that's the real bottom line here is technically it's okay, business-wise questionable. And I'll give you some examples of why that is. Because every time, whether you're Intel, you're Qualcomm, you're AMD, or whoever, anytime they're designing in one generation technology, there's a huge amount of effort to determine when they should switch to the next generation. It's all about the business. It's all about how they can make more money and how they can make more margin, right? It's all about business, not about technology. So this chart sort of captures that because it is a plot of what I call cost per gate or cost per function as a matter of time. The purple straight line here is a 30% a year, 29% a year decline. Historically, that's been the case for the industry. If you take any given technology node, for instance, 45 nanometer, it starts off being pretty expensive. Why? Because it's not a mature technology, you don't have the learning curve, so you introduce the technology at a high cost per function. Over time then, a huge team of engineers gets together and tries to reduce the cost per gate. You do that by improving your processes, improving the control of the process, how well it runs, how smoothly it runs, go down the manufacturing learning curve. So that's one part of it. The other part is to reduce the number of defects per square millimeter. And while both those things happen, then for the user, the cost per gate keeps going down. And until over time it just flattens out. So let's say that's a classic shape of a curve. And this got introduced in this time frame. 2 years later, there will be a new technology node that will again start up at a higher curve. And it's a matter of when this transition occurs, when the crossover occurs. So if you're the CEO at Qualcomm or Intel, you're watching this like a hawk, and you're predicting that this is when it's going to switch over. Therefore, your designs, you got to start the design earlier, right? You start design here and switch over your production to the lower cost technology at that point. That's the fundamental point of this curve, is to show you how those transitions occur. And traditionally, they've been happening every 2 years. The next generation technology is more cost effective to ship product on. So very important business decisions. Engineers, if you're a part of the team, you run like hell to make sure the cost reduction occurs, the transition occurs, the models come up, the design rules come up, the verification comes up. All of those things have to fit together. It's a very complex business, but that's what drives this whole thing, right, is the cost effectiveness of the business. What I tried to show here is somewhere in the 2216 nanometer node, it was getting so much more expensive. Yes, you can find the technical solutions, but it was so much more expensive to do the next generation technology that this curve was no longer crossing over. That adds to the doom and gloom, right? Now people are saying, well, what's the reason to go to the new generation? If this is the way it was, then there's no reason to go to 16 and 14 on this chart. What happens in reality, though, and I think still is happening, is that the foundry in this case would run like hell to make sure that this doesn't flatten out and actually does go down. And to the extent it does, then people will go to the next technology. If it doesn't, you got to rethink what's the best way to build it. Okay? Yeah, so in this case I show that, yes, it does come down the curve, and now you're onto the next generation. So I'll show you some information here. All right, so just to give you an idea how this whole business works, is that it is true that when you go from one generation technology to the next one, the wafer will cost you more. Let's assume it costs you 42% more. Okay? Now, because in the new technology, your linear dimension has shrunk by 30% to your 0.7, you now have 2x the number of transistors, so your relative cost per function is now 0.71, right? 1.42 divided by 2. And that happens to be 29% cost per function reduction. So that's the reason I picked 1.42. It could be whatever, right? Plus or minus. Give you an idea? The idea of this is just to show you how one generation to the next maps in and how you make it cost effective. Any questions? So to summarize, how scaling works is figuring out how the linear transitions work, the design rules, the models, all that stuff. You got to enhance the yield and the productivity to reduce the defects, introduce design for manufacturability, parametric variability control, and we'll talk about wafer diameter increase in a minute here. And then if you're in the fabless model, it's not just the design people, it's not just AMD or Qualcomm or Broadcom doing the designs. You have to work with your foundry because the fab now is across the company boundary. And industry, of course, is very resilient to make sure this happens. So let's give you a little bit background on how this cost reduction through technology scaling works. As an example, for a 180 nanometer technology going to 130, right? Ratio is 0.7. Wafer cost goes up to 1.4. Each side of the die goes from 10 millimeter to 7, let's say, 0.7x. The area of the new die is 0.49, square this, and therefore the die cost on the new technology will be 0.7x, right? Which is what we've been saying. So Intel was actually very good. They're pioneers in this. They had developed a methodology that's called the tick-tock methodology. What it does is that if they were operating in any given technology here, they would create a new design. They would take the old design and do an optical shrink to 65. So let's say they were working on 90 nanometer, they just do a shrink to 65, get that to market. Volumes are low, they can provide it, it's not an optimum design. In the parallel, then they go do what they call a microarchitecture shift, which is to take full advantage of the new technology, and that would be the true high volume runner in that one technology. Then as the new technology is coming up, they would take this design, compact it to the next generation, get the proof of concept, get your reliability tested, on, all kinds of things they do. That'll be the tick, and then they make a talk. Same thing here. So this has gone on for a long time. Some of this, by the way, is reported in my book, so if you're interested in following up, you can certainly look at that. I mentioned to you defect density. So as the new technology is introduced, because it's up the learning curve, you get lots of defects per square centimeter, and then there's huge teams that go try to minimize that defectivity, both physical particles as well as parametric defects. So This is history for technologies that was available. So, of course, industry is now way down here. But the whole idea was to try to minimize the time it took to go from high defect density to low defect density. The shorter the time, the more profit for the companies. So bottom line of all of this is it's all about business. It's all about cost-effective design shipment. It's all about Intel making profits because they're the IDM or Samsung or whatever example company you want to make. Okay, so here's a history of maximum die size. So remember I said there's a limitation. The patterning tool could only handle 10 millimeter on a side for a long time. And so this is a history of how people increased the maximum die size physically, and then what made cost-effective sense. Wafer sizes have been increasing over the years, all the way from 50 millimeters on a diameter in the time frame when I started, and now to 300. The logical next step was to get to 450 millimeter, and that still hasn't happened in production. So it's one of those things that is so costly and not so many people can afford it that the whole industry has to have a change in the infrastructure to support that. So you can ask the question, why do you want to increase the wafer size? Here's a plot that shows as you increase the wafer size, for any given chip size, right? How many more die you can get. It's all about cost effectiveness per die, right? And so this just basically shows you that if the larger wafer costs you 30% more to process, you can get anywhere from 2 to 2.6x the number of die on it, and therefore the die cost on the larger wafer is 50 to 30% better. All about economics. As far as time frame, when the different wafer sizes were introduced, this one is shown as a fuzzy line because we're here at 2017 and still not in production. There are some test facilities, but there's nothing in high volume production yet. Overall, this whole industry operates on the fact that the cost per square millimeter to build a silicon wafer keeps going up. All right, new technology, larger wafer diameter, that cost per square millimeter goes up. But because you have more transistors on the same chip, your cents per transistor keeps going down. If this ever stops, that's when the industry is going to say, oh, we're not going to do any more, right? We're not there yet. Same information from Intel. They're showing you the dollar per square millimeter times the millimeter square per transistor keeps going down, and therefore the dollar per transistor all the way down to 7 nanometer they believe is going to be cost effective. So don't believe anybody yet that says industry is going to terminate at 10 nanometer, right? It's not going to happen. I don't think. I'm not going to bet against it. Okay, so here's the same information from 2011. A gentleman called Paolo Gargini. He used to be the chair of the ITRS for a long time. And he was the main technologist at Intel. His prediction in 2011 was that they were going to continue on this curve. And based on Bill Holt's data, they're still doing it. So I think that part looks good. Point that Bill Holt was also making is that it's not just about the lower cost per gate, but it's also the lower active power. So they're adding to the process changes, changes in the device physics, as well as the circuit techniques to reduce the amount of power that gets dissipated. They introduced these things about sleep transistors, keeping the transistors asleep, for instance, algorithms to minimize the power dissipation as time goes on. In the meantime, though, the industry has recognized that Moore's Law may have some limits, and therefore they have been looking at alternatives. And so there's this thing called More than More, beyond CMOS, whatever you want to call it. So as the industry here was shrinking the base technologies, there's also the beyond CMOS silicon technology, but there's also a new dimension coming up for diversifying additional ways to get more leverage in shipping integrated circuits, or certainly package units, right? And the primary function here was adding analog functions, passives. The biggest one was more of packaging type of activities. And we'll get into that in the opportunities section. So that's for the industry background. Okay, let's cover market drivers. Any questions? You guys are awfully quiet. Some people had me sign already, so you got to ask me the questions, right? Okay, Professor Van der Spiegel covered some of this. One of the big drivers in the last few years, last 5 to 10 years, has been the smartphone. And if you really explore this anymore, it used to be about wireless in the 90s and the early part of 2000. And that was all the wireless activity. Then you had more capability in computing capability on the phone. Where it really took off was in the late 2005 timeframe, where people your generation probably started to get into social media. That's when the whole business took off.